Another theory that helps us figure out the geometry is the VSEPR theory. VSEPR stands for valence shell electron pair repulsion theory. So we're talking about the valence electrons, and we're looking at the geometry created when those electron pairs in the outer shell repel each other. Because they're all negatively charged, they want to be as far away from each other as they can. So what kind of geometry do I get when this happens? So this is also referred to as a molecular geometry model. And our goal, again, is to minimize the number of electron pair repulsions or the strength of the electron pair repulsions. So I want to put those electron pairs as far away from each other as possible on the central atom and on, if I can, the other atoms in the species. So the geometry of these species depend on how many atoms I have in the molecule and on the number of pairs of electrons that are attached to the central atom. Central atom is key in determining the geometry of these species. So we're going to look at 5 different geometries: linear, trigonoplanar, tetrahedral, trigonal bipyramidal, and octahedral. Each of these is associated with a certain number of pairs of electrons attached to the central atom. I determine the geometry by drawing the Lewis structure, and I count up how many electron pairs are around the central atom. I've got some compound examples, and here is the chart that shows us what things look like. So if I have 1 pair or 2 pair of electrons, 1 pair means I only have 2 atoms, 2 pair of electrons on the central atom, either of those cases I have a linear molecule. So in each of these diagrams, A is the central molecule, and the gray teardrops are the pairs of electrons attached to the central atom, forming bonds with the outer atoms. So I have molecular model pictures of what these things look like. My guess is you went through these things in your first year chemistry when you were dealing with geometries. So you should know these. You should know the number of electron pairs and what VSEPR geometry that generates. So what happens when I have multiple bonds? How do I deal with that? Let's look at carbon dioxide and see if we can figure it out. Carbon has a valence of 4, oxygen has a valence of 6. So we have 12 plus 4, so I have 16 electrons. I have 8 pair of electrons. Carbon is a central atom. Oxygen is attached to carbon. So I draw the atoms, put in my bonds. So that takes care of 2 of my 8 pair. I have 6 pair to go. So if I put in lone pairs on oxygen, so now I have 6 out of my 8 pairs done. I'm holding off on the last 2 pair because I'm not sure exactly where they need to go. Both carbon and oxygen need an octet. Right now, nothing has an octet. Oxygen's closer. It has 6 electrons, 3 pairs. I need to put my last 2 pairs of electrons so that both carbon and oxygen get the octet. The only place to put them so that'll happen is to make oxygen double bonded to carbon. So now oxygens have an octet, carbon has an octet, and so we're satisfied. If I build this molecule and look at its geometry, what I'm going to see is this is linear. So when I'm determining the VSEPR molecular geometry, when I'm dealing with multiple bonds, there are a couple of things that I need to keep in mind. Double bonds I treat as a bond. So I have 1 bond between the carbon and the left oxygen, 1 bond between the carbon and the right oxygen if I treat the double bonds as a bond. And if I go back and look at my chart, when I have 2 bonds, then I have a linear geometry. So how do I deal with the geometry if there's no central atom? So then what I have to do is find the geometry of each interior atom. An example of that would be hydrogen peroxide. Again, oxygen's 6, so I have 12. Hydrogen's 1, so 12 plus 2 is 14, so I have 7 pair of electrons. And the structure is hydrogen bonded to oxygen, bonded to the next oxygen, bonded to hydrogen. Again, because I don't have a central atom, I've got to look at the geometry of each of the oxygens. So there are 3 of my 7 pairs. I need to put 4 more pairs in. Hydrogen can't take any more electrons, so let's see if we can put the remaining 4 pairs of electrons on the oxygen. So now I have 7 pairs. That works. So if I look at the oxygen, I have 4 pair of electrons on each oxygen. So what that means is the geometry of each oxygen is tetrahedral. So this is a case where I can't give you the geometry of the entire molecule, but I can give you the geometry around each of those oxygens. All right, VSEPR theory is pretty good. It is a model, but it doesn't cover all the bases, because VSEPR theory assumes that the electrons in the atoms don't change. So the atoms don't change, the electrons don't change, and everything is the same. We take a look at methane. We have a central atom, carbon, and then 4 hydrogens surrounding it. Hydrogen has one s electron. Carbon has two s electrons and two p electrons. So if we're going to do the orbital diagram, it'll look like this. First of all, we have to remember that this s orbital has a lower energy than the p orbital, because the p orbital is more complex in shape. That gives it the higher energy. Because my s orbitals and my p orbitals have different amounts of energy, that should lead to two different kinds of bonds between carbon and hydrogen. It turns out, if I measure them, all the bonds in hydrogen are equivalent to each other. So here's my orbital diagram. This is the orbital diagram I'd expect if I'm dealing with VSEPR theory. For carbon, I have 2 electrons in the 2s and 2 electrons in the 2p. With this geometry, though, I can only form 3 bonds. And the s orbital contributes both of the electrons for the bond. The p orbitals contribute 1 electron for the bond, and they're depending on hydrogen to create the other electron for the 2 electron bond. But this would mean that I could only form CH3, and one of the hydrogens would have to come to the molecule with no electrons, and that doesn't work. So something else obviously is going on top of which all of the bonds in methane are identical. This certainly doesn't give us that arrangement. So what happens is I deal with something called the hybridization theory. And when atoms combine to form the molecules, the orbitals of the atoms hybridize to create the correct number of bonding orbitals, and these bonding orbitals are equivalent in energy. So if we look first of all at the shape of the s and the p orbitals, s orbitals are spherical, and they're represented in red here. P orbitals are figure 8 or double sphere geometries. They're going to be represented by blue shapes. When I hybridize them, I blend the 4 orbitals together, so I get 4 new orbitals. So however many orbitals I put into the blender, I get the same number out. And because I'm taking a p orbital and s orbital and combining them, what happens is I get an unbalanced or a lopsided figure 8 hybrid orbital. And the name of the orbital is based on what goes into forming it. So for these orbitals, I have 4 hybridized orbitals. And to get them, I took an s orbital and I took 3 p orbitals. So I end up with a total of 4 orbitals, and I name them based on what was used to make them. So they're called sp3 orbitals, and they all have the same energy. So if I put them together to form a molecule, what I get is something that is tetrahedral in geometry, because there are 4 orbitals, 4 bonds attached to the central atom. So if I look at orbital diagrams, p orbitals have higher energy. In the carbon atom, there are 2 p electrons, and there are 2 s electrons of different energies. When I hybridize these, I get 4 orbitals, all of the same energy. Each of them has 1 electron, so each of them can form an equivalent bond with hydrogen. And when I look at methane and analyze the bonds in methane, what I see is 4 bonds that are identical in energy, and therefore the theory that gave us this, the hybridization theory, is a good explanation. Okay, sometimes I don't use all my p orbitals for hybridizing. The geometry changes then. So in this particular instance, I have 1 s orbital and I have 2 p orbitals. I put 3 in, so I get 3 out. And when I combine these, this is called an sp2 orbital, because that was what was used to make them. And I get 3 of them. They're all equal in energy. And so when they form a molecule, they're all on the same plane, and so I get a planar arrangement, and it's a trigonal planar because I have the 3 orbitals. I can take the s orbital and only 1 p orbital. When I combine them, I get 2 hybridized orbitals, and because I used 1 s and 1 p, it's called an sp orbital. And when I combine 2 sp orbitals, what I get is a linear arrangement. So there are a variety of ways I can hybridize atomic orbitals to get molecular orbitals. And each way I do it gives me a different geometry. So here's that same chart we looked at before, but now we're adding in hybridization. So when I have 2 electron pairs on the central atom, I have an sp hybridization. 3 electron pairs, I have an sp2 hybridization. 4 electron pairs, sp3 hybridization. When I expand my octet, so this is 5 and 6, I bring the d orbitals in and use them as sites where electrons can be to form these additional bonds. I've used up all my s orbitals, I've used up all my p orbitals, I need something else. So therefore these can only form when I have atoms, central atoms, that have d orbitals available to them. And so when I have 5 pairs of electrons, I take advantage of 1 d orbital and throw it into the hybridization mix. If I need to have 6 pairs of electrons on the central atom, then I need to use 2 of those d orbitals. And just a reminder that the energy of these hybridized orbitals is always between that of the original orbitals. And for 4 of the 5, so for sp, sp2, sp3, and d2sp3, the orbitals have identical energies. Because dsp3, or trigonal bipyramid, has a planar portion and a linear portion, the orbitals in the planar portion have 1 energy. The orbitals in the linear portion actually have a slightly different energy. But the other 4, all the orbitals are identical in energy.